Hello students, welcome back. Let's begin section 3, interval estimation for population means. Wait a minute, haven't we done this before? Back in section 1, we went through this problem, remember? We went through confidence intervals and confidence bounds for the mean one-way commute distance of all commuting students. All commuting students, remember? So this is an interval estimation for population mean. But then again, why are we repeating it in section 3? Well, that's because we went through one type of problem, but there are others, and we didn't exhaust all there can be. Oops, excuse me. Here is a basic summary. From simple random sampling, if we have large samples sufficiently large, then we can apply the normal approximation. But if the sample size is small, then what we do? Well, that's a problem, and we have to answer this question. By the way, why does the normal approximation apply for sufficiently large sample? The reason is because of the central limit theorem. No matter what probability distribution that we begin with, if you take an independent repetition and take the average, and then the distribution of the average more or less follows a normal distribution of the mean mu and the new standard deviation sigma over square root of n, which we call the standard error. More or less. So this is an approximation. And approximation converges at n gets really, really large. So if n is sufficiently large, the sample size is sufficiently large, then we have pretty good approximation. And typically in real life situation, 100 or more, then we'll say it's okay. If you read some old textbooks, sometimes people say 30 or more is sufficient, but no, that's so 20th century thing. I mean, in 1920s, 1950s, 1970s, yeah, but nowadays we expect more from computing power. So 100 or more, then we use normal. And 50 or less, then we consider sample size is too small, so the normal approximation is not going to be very good. And between 50 and 100 is a kind of gray area. Depending upon what your error tolerance is and what the circumstance, we can do one way or the other. In my exam problem, I'll try to avoid those kind of things. So, for a large sample size of typically 100 or more, normal approximation, due to this. Now, what if the sample size is smaller? Well, here is a complete picture. Simple random sampling may have large sample or small sample. Large, typically 100 or more, then we have normal approximation. Okay, great. If we have small sample size, then we have to have the next question. And this question can be a bit restrictive. Is the original population normally distributed? If no, then, well, you just have to go back and redesign and take a large sample and then apply the normal approximation, because we can't really do anything that works in general. Maybe we can do something for some special circumstance, but not in general. So the answer is no, then we have to go back and take large sample, and then you have to do the normal approximation. Now, in some cases, as a matter of fact, in a lot of cases, the original population distribution is normal. In that case, if yes, then depending upon the next criterion, we can use either the normal distribution or something new, the t-distribution. For known population standard deviation, if sigma is known, then you can use the normal distribution, the z-distribution. Unknown sigma, then you have to replace sigma by sample standard deviation. In that case, we have to use something new, t-distribution. And what is this? Well, we're going to talk about it in a moment, so please be patient. So in short, the t-distribution is used for small samples with unknown population standard deviation, and when the original population is believed to be normally distributed. And the last question here, that can be rather restrictive in real life situation, but in classroom, this doesn't really do a thing, because whatever problem I give you in the exam or in homework, it should work. So if you have large sample size, then use normal. If it is small, then it's going to be either normal distribution or t-distribution, depending upon sigma values. Do we know sigma or no? So this question, even though it is important step, especially if you step outside of the classroom, but for now, for the class itself, this doesn't really do a thing. Well, what if the original population is no way close to normal? As a matter of fact, we went through one such example. If you have binomial proportion, or as a matter of fact, if the original is Bernoulli, then this is no way close to normal, so small sample size will not do. So you have to go back and redesign so that you have sufficiently large sample size, typically 100 or more, but in real life situation, typically 1,000 or more. All right, now let's consider how to work with small sample size. Here's an example problem, and please stop the playback and read through. So, which random variable shall we use for these kind of problems? Well, the first problem is the same as the example problem that we discussed in section 1. I specifically emphasized population standard deviation and color-coded accordingly, otherwise the same. Larger sample size, and then we know the population standard deviation. What we use? Second problem, large sample size greater than 100. We don't know population standard deviation. We only know the sample standard deviation. What do we do? Small sample size, less than 50, so just 26. We know population standard deviation, and furthermore, the original distribution is believed to be normal. In that case, what do we do? Finally, small sample size, the original distribution is believed to be normal, and we don't know the population standard deviation, so we are using sample standard deviation. What do you do here? First three, you can use the z distribution, the normal approximation. These two, the first two, those are normal approximations. We don't know whether the original population distribution is close to normal or not. It's just that for large sample size, we are doing normal approximation through a central limit theorem. For C, this is not an approximation because the assumption is commute distance is normally distributed. If that's true, then you can just use normal. This is not an approximation because original population distribution is normal. It's just that we have sample size of 26. So instead of just sigma, you have to use SE as sigma over square root of 26. Finally, this one, D. That's going to be t-distribution problem. All right? Small sample size. Original distribution is normal. But in practice, that's not what you focus upon. We know only the sample standard deviation. Okay, we went through some decision-making exercises. Now, I mentioned t-distribution several times. I have to talk about what that is. Let's see. Here's a review. I mean, large sample size, normal. And then this question is not really practical for immediate purpose because we are talking about classroom examples which will have answer one or the other. So known sigma, normal, unknown sigma, t-distribution. So that's the only case we have to use t-distribution. And how does it work? T-distribution has something called the degree of freedom, and that's n-1. N is the sample size, we do n-1. Why -1? That's related to the fact that we are doing one-dimensional statistics only. If you go over to multivariate and say, for example, two-dimensional, in that case you may end up with n-2, and that's as much as we go even in 3000 level statistics course. In 4000 level we may go a bit further, but in 3000 level you go up to n-2 even for highly sophisticated case. But this is 1000 level, so every single time you just do n-1, and we get something like this. So the normal curve is this red dotted curve, and the t-curve is this solid blue curve. And as you can see, the t-curve is symmetric and unimodal and all, but has more spread and less concentration towards the center. And let's manipulate this a little bit. Currently, the degree of freedom is 1, so sample size is 2. Now let's increase the sample size. Step, 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 step. What's happening? As I increase the sample size and consequently the degree of freedom, the t-curve, the solid curve, is approaching and converging into the z-curve, the red dotted curve. Now, if you go over to, much higher degree of freedom, then they become rather indistinguishable. And also, let me keep the picture. And also, the same standardization formula applies. In this picture, we do n minus center over SC. For Z or for T, exactly the same, you see. So this formula is called the formula number 1, applies for Z, applies for T, and applies for various cases. As a matter of fact, n minus center over SC is that important. All the more reason to be called the formula number 1 in terms of the level of importance. All right, I talked about pretty much everything that I needed to talk about for now. And let me just show you some pictures for some indication for what to do next in a separate video. Here is a visualization of a confidence interval. Do you see the gray curve as a background? That's a normal curve. And then the solid colored curve is a t-curve. Here, the default is sample size of 5, so degree of freedom is 4. As you can see, the t-curve is more spread out, and z-curve is more concentrated toward the center. You see the difference there? Now, do you see this dotted line here and there? From here to there, that is the confidence interval, 95% confidence interval for the z-curve. If you use a t-curve, then the confidence intervals are wider, which means bigger margin of error, you see? If you're allowed to use the z-curve, then you have smaller margin of error, so your interval estimation is better. But if you're theoretically not allowed to do that, then you have to make a compromise and then use a t-distribution. That'll give you larger interval of it'll give you larger confidence interval and therefore larger margin of error. If I increase this to some higher sample size like this, 50, then as you can see, they merge very close together each other. And then if I go to say something like 10, then somewhere in between, you see. See some difference there? So we're going to do some confidence intervals and also confidence bounds as well. We'll do all those, but we're going to do those in a separate video.